Okay, where are we? I think this time we're gonna do convolution. We're gonna convert the functions, the convolution function to CUDA. Okay, so we need to know where we were before. Get mean squared error, index map copy, and kernel index map copy. Yeah, get rid of reverse. Okay. Oh, pooling. Actually, yeah. After copy comes pooling. Pooling forward and pooling reverse. Pooling works basically the same way as the copy function. The only part we need to copy is this part right here. So we're just gonna copy and paste from the kernel copy. You just copy it. Oh, index map. What am I doing? Oh, yeah. We have a lot of stuff. We have a lot of stuff copy. Index map copy, and just copy and paste and change the names. Okay, what do we call it? Index map pooling. Index map pooling 2D forward. Okay, index map. Oh, we wait. Yeah, index map pooling 2D forward. Okay, just change the names right here. Index map pooling 2D forward, and change name back here. Everything else here should be exactly the same. So I'm not sure if I'm missing anything, but if we are, then we'll figure it out. Okay, what is required? For I equal index width, for I equal index height, we need to understand everything we're doing here. Kernel pulling into the forward. Again, it's a two-dimensional array. The result length and result count. For each image, no, for each slice of the image, and for each slice of the two-dimensional array, and for each image, for each pixel within the slice, you do a calculation. And this is the calculation we're doing. We need to know where we are within the image and select if the index is matched. And then for each pixel in the source that does something, and we add them up and we copy them. Okay. Oh, where are copy? Let's not get lost here. Okay, we need to change this part right here. Okay, we need to know which part we are changing exactly. For J, oh, this could get complicated. Okay, I. If we copy the wrong thing, we're in trouble. I don't think we need counter. Okay, we have to make sure we get the right stuff here. Okay, type ABS. Let's just make sure we don't. Oh, does K equal I? Yep, counter. We don't need counter. We need a next. We don't need counter. Just make sure that everything is the way it's supposed to be. Okay, for J. So far so good. I don't think I missed anything. I'm just trying to visually figure out if I missed anything. If I less the result length. Whoa. If J is less than result count. Okay. I J result index source length. K equals I sum equals 0 for I equal index width. Now we go into the index and then summing up all the pixels. No, not summing them up. Just going to the index and finding out which one sum equals the maximum. Sum equals maximum. We can't call it max, so that's why we call it sum. And yeah, so far I think I got this right. Pulling to the forward, everything else is the same. No real difference from scaling. So just make sure that everything's right. Yep. I'm pretty sure this one's right. Now let's do pulling reverse, which should be slightly more complicated. If not complicated, at least different enough that we need to think about it. Okay, pulling to the kernel, pulling to the reverse. Okay, reverse. We have to rename everything. And reverse. No, to the reverse. Okay. Now, we need to verify what we need to change. I don't know yet, so let me just read this and figure out what's different. Pulling to the reverse, what is different? For I equal index width, for j equal index height, and source and result. Oh, let me just think about this for a moment. Most everything is the same except for the output part. That's the part I forgot. CUDA neural unit outputs. We need to make a slight modification in reverse. Source, result, outputs. Okay, now to CUDA neural unit copy. And let's do everything one step at a time. Add outputs. We don't want to get this wrong. Outputs. And then there's a check somewhere. Oh, we should have copied everything. Okay, there's a check somewhere. Source. Whoa, I didn't change that one. That's a mistake. Outputs. No, not source. Outputs. Okay, parent length. Everything else is mostly the same. Is shape compare. We have to shape compare outputs. Outputs and source have to be the same shape. Source count not equal source count. Oh, there's a lot of little details I need to change. I'm gonna do the cosmetic stuff later, but for now, let's keep everything simple. Shape compare source, outputs that way shape, everything's the same. Little cosmetic stuff. Okay. Outputs that way data. Right now, we're only adding outputs. The complicated stuff is gonna come later. Right now, we're only adding outputs. Okay. Now let's do the complicated stuff. Okay. For I equal index width, no, we don't change any of this. Sum, counter, and we take all of this, just this part right here, inside the loop, because the kernel doesn't bother with most of the loop. Pulling to the reverse, sum, and okay, so counter, unsigned long counter. We need a counter. Okay, counter equal the index of the thing out that we are copying. Let's just make sure everything works. Source length. Make sure everything is the same. We don't have to redo this. If type ABS. Okay, let's go back to what everything says. For I equal index height, for each pixel in the square that we are selecting, find the index of the pixel inside the index inside the source, and then compare the output with the absolute output, and then set the counter to that specific pixel. Okay, now that we have the counter, then for I equal index map, we just go to each pixel in that particular region. We divide the height of the index map represents a region. If the counter equals the selected pixel, then we set source to result. There's only one result for multiple sources. Okay, we don't need this part right here. Okay, we set source to result, and for every other we set to 0. So that's backpropagation and pooling. Kernel pooling, index map reverse. Everything's the same. Why is it making an error here? Global location, global. Yeah, it doesn't matter. Okay, so far so good. Okay, index map pooling reverse. Everything's the same and it works. Now for the hard part. Okay, let me rephrase that. Now for the really hard part. Okay, convolution. This is going to be really painful. Let me pause and see if I can figure this out in my head. Actually, from the looks of it, it looks slightly easier. Ooh. Let us copy it and see what we can do with it. What we can do with this. Some parts of it looks like it could be easier. Or it could be much harder. Okay. Let's just modify everything one by one. Okay, step 1, copy this part. That just let us know visually where we are. Static, replace static with global. No, not global. Device. That tells the CUDA that this is a function that operates inside the GPU. Device. Type CUDA null unit. Let's just change CUDA null. We just need to change the names. We shouldn't be seeing any problems until later. Okay, index. Let's just change the name because we need the name kernel for something else. Index map convolution to the value. Change name. Just change. We need to change as little as possible because otherwise it's gonna get really complicated real fast. CUDA null unit. We keep everything the same. And CUDA null array. CUDA null. CUDA neural. CUDA neural. I don't want to redo all this. CUDA neural. No, CUDA index map. No, CUDA. Did I remember to change that? Because you really don't want to get this wrong. Type index map versus type CUDA index map. That would be a really big problem. CUDA index map. Okay. Okay. Oh, something else I need to change. CUDA index map. Kernel pooling. No. Where are we? We get back to where we were. Okay. Index map convolution value. I'm pretty sure we don't need to change anything here. Convolution value for I. For every item in the index, do the convolution, which is sum equals source times filter, the corresponding filter pixel. Everything same, everything works. Okay. Now for this part right here. Okay, CUDA null, just keep everything the same. So far here, this is fine, this is fine. And now we get to this we have 3 for loops, but we can only use 2 of them. This is a thing when converting from a CPU memory to CUDA memory. You cannot use every single for loop you can turn every single for loop into a kernel. Okay, the reason we cannot turn this one into a kernel because we're summing up pixel by pixel. Kernels are only supposed to be used when you operating on a single pixel, on a single slice which is independent from all the others. Because if two kernels have to share the same memory, write the same memory, then you start having problems. So they have to be completely independent. So this part right here has to be excluded. But these two for loops can be put into kernels. So we need a 2-dimensional kernel that for J and K. Okay, so should it be J and K? Oh, yeah. This is gonna be not that easy. Just wow. Okay, now I need to figure out how to translate this into something that actually works. Oh, device. I just copy this. Hopefully, I can make something work with this. I don't want to write everything from scratch because that would just be way too complicated. Okay, let's start eliminating stuff. We don't need this. We need I and J, but we don't need this other stuff. If J equal result count, result length. Okay, let's make sure. Now we don't need this part. Get rid of this part. Okay, let's see what we can keep and what we need to get rid of. I and J is the X value. Oh wait, we're using J and K. Okay, let's change this from IJ to JK. But we need to be clear about which one is which. Okay, for J equal count. Okay, J equal result count. Ooh. Yeah, J equal result count. We keep this. We keep the J. Whoa, whoa, whoa. Oh, yeah, J, K, and move R on top, just to keep things consistent. Unsigned long. All right. The point is to keep everything as close to this as possible. Just convert those two for loops into kernels. Okay. The kernel works by itself, so this function. Oh no, we need to change the names. Index map convolution to the forward. Index map convolution to the forward. Index map convolution to the forward. Let's just continue. Kernel array index map convolution to the forward. That's a long name. Is it even worth it calling all that? Yeah, no point changing now. That would just complicate everything. Convolution to the convolution to value is we keep that separate because putting it in here will just complicate things. So have a separate function just so we don't have to deal with this. Okay, if I equal result length, not I. If j, which one's which? We have to make sure which one's which. J equal result count. Okay, j equal result count, and k if we need to make sure where we are. If k more than or equal result length, is it the same? Result length. Okay, you have to make sure everything's where it's supposed to be. If k more than or equal result length, k plus plus. Okay, result count, result length, source count, source length. We also need filter. Let's not forget filter. Result count, result length, filter length, no, filter count. Just to make sure we're not missing anything. Oh, do we need filter? Yeah, filter. Yeah, I need to add this. Maybe we don't need it specifically, but making sure it's there uh, simplifies everything. Just to make sure we're not missing anything. Filter. Filter count, filter length. Is that necessary? Oh, it's not necessary. Result. Or maybe actually this is necessary. Result length, result count is necessary. Even if we don't use it. Okay, let's just make sure everything's the same because this is gonna get very complicated later. Okay, convert the for loop for I equals something k plus plus. Okay, now we copy this part right here. Result. Make sure we're not missing anything. Okay, what do we need this? I'm not sure if we do. I don't think we need this filter. For I equals source count. We absolutely need this. Source dot array data. There's no array data. Filter array data. The index map. Where's index map? Oh, index map. Yep. Not index map. Array data. Index map. Index width. Index height. Whoa. Oh. Ah. Index width. Index height. And index map, not index data. That's why I called it here. Index map. And get rid of this. Okay, why the k? Okay, k. That's why I used it for. K is the index offset. So what we're doing is for each image in the source and for each pixel in the image, we do convolution just that one pixel. That's what convolution value is. We do convolution just that one pixel and we return a sum and we return the result of convolution. And in this right here, we take the sum of all of each one of the pixel and add them up. And at the end, we put the result inside the index right here. Okay, j equal result length. Let's just make sure we're getting everything right. Is there a result index? There's no. We calculate the result index is somewhere else. Okay, we don't need that. Source index. Oh, is it result index? Okay, we're missing something here. There's a result index, which is j times result length. Ah, there's a result index. We've already calculated. Okay, we're making a few changes here. Let's just make sure we know exactly what we're doing. There's a result index. What else do we need? We need a source index. Okay, source index is source length times I. But we don't want to do too many multiplications. That just slows everything down. Okay, so yeah, source index starting from 0. We're going to all of them. So let's just set this as 0 and then using source index here. Source index. We don't want to do any multiplications here. We're already getting speed and then add it up here. Instead of doing multiplication, we're just adding up. The size of the image. So now source index plus equal source length. We're going one image at a time, so we simply add up the size of the pixel, and the whole thing will take care of which pixel we need to do. The index is already done. Filter. Oh, we forgot filter. Source filter. Source result filter. We don't need outputs. Filter. Source filter. And yeah, we don't need that. Source result filter. Okay, we're confusing ourselves here. Filter index. Filter index equals what? Okay. Let's see. J times source count. Okay, so we're just copying everything we did before. J times source count plus, is there a plus? Oh no, J times source count times filter length. Oh, let's not forget that. Oh, that would be bad. Times filter length. Because the filter array is a three-dimensional array whose depth is the size of the source is the depth of the source array times the depth of the result array. The number of images in the source array times the number of images the number of images in the source times the number of images in the result. So there's a filter for each combination of images. For every image, there's a number of indices that's the corresponding. Oh, that's really confusing. I will figure it out. Okay, J times source count times filter length, filter index. Okay, now for each item in the source index or in the source count, we do index map convolution value. Source times filter, index width, index map, source index, source length. Do we need source length? Yeah, source length, source count, filter length, filter index, not filter index, filter index. Which specific index we're using? Okay, which specific image in the filter array are we using? Source index plus equals source length. Oh, we need filter index plus equals, okay, filter length. Because using it, we're doing the horizontal. For the backpropagation, we have to do vertical, but we'll deal with that later. Okay, so far so good. So far so good. Okay, and result time filter index. Oh no, it's not just filter index. It's filter index plus k. Because we have to specify which specific pixel we need. Filter index plus k. Okay, so far so good. Let's just make sure we didn't miss anything. Kernel array index map convolution. Okay, index map convolution to the value. Okay, what are we doing? Okay, we take one single pixel in. we select one pixel in the first image, and then in the result image, and then for each corresponding pixel in the entire array of source images, we do a convolution on that particular pixel, and then sum everything up, and then sum is put right here. Okay, so far so good. Oh, we don't need counter. Do we index? We don't need index either because I'm using it here. Okay, IJK. Make sure everything makes sense. Let's move that down here just to make it look better. Okay, IJK. Awesome. We're just copying everything. Okay, now for the slightly less hot part. Okay, well, let's do it up here because I don't want to have to figure this out again. We need to know exactly what we're doing. Okay, we need to convert this for loop into a kernel call. Okay, J kernel count, result count. Okay, if we forward, result count. Oh, did I get backwards? No. Oh, that's because of the way we're doing things. We have to do count first, and then length. Okay, we just have to do everything in the same order that we did it before. You don't want to change anything. Okay, kernel map. I just copied the entire name. Okay. Now make sure we didn't miss anything. Kernel. Let's copy everything just so we can see what we're doing. Make sure all the calls are the same. I'm just copying just so I know where everything is doing. Source. No, result, source, filter. And then index map stuff, result, source, and now result length, source count. Result length, result count, source length, source count, filter length, filter count. Okay. Otherwise, it's going to get really difficult. Okay, let's see. Are we getting it right? Yep. We know that. Make sure I set all the variables to the way it's supposed to be. Result length, result count, source length, source count. Okay, filter length, no, filter depth. Okay, filter count not equal source length or source count. Index width not equal result length. Index height not equal filter length. And yep. And we can get rid of this. But it's not over yet. Now, we have to do all of this, but backwards. Actually, it should be the same basically. Index map convolution reverse. Okay. As far as I can tell, everything should be the same. Well, almost everything except we're reversing source and result, and not pooling. What am I doing? We take everything here and copy it down here. Oh wait, almost everything here. Let us copy it anyway, but we're gonna remove the convolution item, convolution value. Okay, this part right here we don't need because we just use the same one from out there. But now we need to change convolution reverse. Just change the names, just so we don't forget. Let's do that first, because otherwise you risk forgetting. Now convolution reverse. Since I included everything, not reverse. Okay, let's just make sure we don't miss anything. Reverse. Okay. So far, everything should be exactly the same. And we keep the parameters in the same order. So let's just make sure, let's just see what we changed. Convolution to the reverse. Okay, so everything's the same except we replace source with result. Okay, for I and K, we didn't change much. Source count, just these names right here. Source count, source length, result count. So let's just change what we changed. Okay, source result count, that's the first for loop. Replace with source. Result length, source length, and oh no, everything's the same. And up here, let's see, make sure everything's the same. The third for loop is for result count. Ooh. We are in reverse. This is complicated here. We have to make sure everything's the same here. Result length equals result. Result length. Source length equals I times j. Filter length. Oh, I'm complicating myself here. Okay, let's just make sure we didn't miss anything. Okay, we're in reverse. Everything's the same. This part is right here is the same. I'm pretty sure. Oh no, wait. Because we're going I and j instead of j and I. Because I is always used for the source. If we're looping to the source, then it has to be I. If we're losing to result, it always has to be j. The k is always the same. So step one, move this one up here. Because everything has to be reversed. The j stands for the result index. If j equals this to result count, if I is source count. Oh, now I'm confusing myself. Source count. This is just a convention so far, but it's important we keep everything. Okay, so if k less than source count. Okay, k is the same. So there shouldn't be any problems here. If for k equals source length. Now, this multiplication here. Result index equals 0. Let's modify the result index equals 0. And that's why source index equals I. We have to be careful which one we are using. Okay, result index starts from 0. Oh, that's when the forward. Why when they were forward? Result index starts from 0 and then multiplies and then goes from 1 to the from 1 to I. Okay, we're trying to transit everything as closely as we can here. Filter index equals, it's still equal j, I think. Does it equal j? Filter index equal j times source count. Whoa. Okay, why does it equal j? Let me try to figure this out. Oh, because we're starting at the top. J is 0, so it's starting from at the top. In the forward pass, we're going horizontally. In the vertical pass, we're going vertically. That's how we do the dot product. It's a dot product times a convolution. It's a combination. Oh, j equals 0. Filter index equals not 0. Filter index equals I times filter length. Oh, wait. It's I times filter length is I times filter length. Now I remember. We could still do the we're doing the first one, and then we have to add a certain value to everything, because we're going backwards. No, not backwards. The same way we do here, filter index plus filter length, because it's horizontal, it's just one step. But here we have to jump a certain number of steps. How many steps? Unsigned long. Filter jump equals filter count. No, it's source count. Okay, source count. Okay, times filter length. Because we have to jump a certain amount that's corresponding to the number of the size of the number of images in the source times the length of the filter. Okay, now what are we doing? Filter index plus equal filter count. No, filter jump. Okay. This is really getting complicated here. Okay, result index plus equal result. We're not jumping here. Result index. We have to make sure we're not missing anything. And I need to do everything one step at a time, because otherwise I'm going to lose myself. A lot of the things that are not necessary when we're doing this normal. Here we just do a multiplication and that tells us exactly where we are. But here we cannot do a multiplication because we're inside kernels and doing multiplications. It just slows everything down way too much. Okay. Let's just go to everything one step at a time. K less than source length returns 0 because we're doing 1 pixel at a time. Okay, force length, the convolution, everything here for I equals source count, because that's how it is up here. For I equal source count. Oh wait, it's not source count, it's result count. To the reverse. Oh, we're going to each pixel in the result count. Okay, let me not lose myself. For j equals result count, not for I. Just copy and paste, just so we know that we didn't miss anything. For j equal less than result count. Where are we? I'm losing myself. Okay, it's the source, I think. Yep. Result source. I'm just trying to make sure I didn't mess myself up here. Source the source index plus k equals sum. Result index plus equal result length. Let's just verify everything. Everything is the same. For I equals source count. For k equals source length. Sum, everything is the same. For I, k right here. I source count, k source length. We're just doing everything as in this for loop. Less than equal for source length returns 0. Result index equals 0 because we're going vertically. Result index plus equal result length. Source index equals I times result length. Filter index equals I times filter length, because again we're going vertically. We're starting from the first row and then going down a particular column. That's why filter jump. Source content filter length, so that's why we're going down. Result filter instead of source and filter. Index width, index map. K is the particular pixel we're dealing with. Result index, result length, filter index, filter length. And yep. If filter count, if index, oh wait, if index map horizontally equals source length, not result length. This is important. We're reversing everything. That's what just to make sure we don't go over the limit. The source length and the result length might be different. Usually they should be the same, but they might be different. So just to make sure. Okay, source length, convolution reverse. Everything is all the values are in the same order and mean the same thing, so we don't need to change anything here. Okay, that's pretty much it. I don't see any errors. When we start the testing, if there's any error, we'll find it. But so far everything looks to be identical. Okay, this is what you need to do when doing a kernel call. It's exactly the same as a for loop, but you have to verify where you are within the for loop. because we're doing threads. Oh, no. There's a mistake. Source index equals I times source length. I'm sure there's a lot of these small mistakes out here. Filter length source count, because everything, we're still starting at the top. This is right. For G equals result count, everything the same. Result K, result index, filter index, and that's it. Yep. Okay. Let us compile, and just to make sure we didn't make any typo mistakes, any of those stupid typo mistakes. I'm sure it makes some other kind of mistake, but let me check this out. This is another small mistake. Type ABS over here. CUDA doesn't know what that is. FABS, but it's not. Oh, FABSS. FABSL. It's not FABS. FABABSF. That's the one we need to use. FABSF. That's the CUDA version. FABSF. Because CUDA functions have a very limited amount of functions, of standard C functions, so we can't just use anything. Okay, so it worked. I've also made a few cosmetic corrections here, but otherwise everything compiles correctly. That does not mean that everything's correct. So we're gonna have to test everything, make sure that it works correctly. But so far, everything looks good. Let us continue with our translation, and then eventually we'll be ready to do an actual test. That's enough for tonight. We'll do that tomorrow.